Happy Tuesday.
So a quick note on what I planned for this week. I unfortunately spent pretty much the entire break in bed, so I couldn't get to recording the double integrals. So it's going to do rectangular, the general regions, and polar today. I'm going to take the entire class on Friday. I'll do the entire 75 minutes. So I'll try and get through all three of them this week. So that's the plan. Double integration over rectangular regions. So we're going to evaluate the double integral of 4x plus 4y plus 16 over the rectangle 0, 2 cross 0, 2. I'm not drawing the scale. Zero, 2 cross 0, 2. This is read that the x-axis goes 0 to 2. The y-axis also goes 0 to 2. So there's our region. There's a result for multiple integration. It's known as Fubini's theorem, which says the order of integration does not matter. dx, dy, dy, dx. You'll get the same result as long as you set it up correctly. For rectangular regions, the setup is really simple. All right, I'm going to start thinking more of general regions as well. So when you set up your iterated integral, you first want to decide your order. Do you want to do dx dy or dy dx? Because that decides how you describe the region. Rectangular, like I said, really doesn't matter. So I'm just going to stick with the standard dy dx. Right, that means dA becomes dy dx. Right, remember, dA is the differential for area. And then here's how you think about it. And this works perfectly because I can just use the ruler. You draw an imaginary vertical bar. And you let it run throughout your region. Since we're doing dy, you're going to let it run horizontally throughout the region. And you go, okay, what does that bar extend from? Well, it goes from 0 to 2 over the entire region, right? So those are your bounds for y. Bounds for x are going to be, was it ranging from horizontally? Well, again, 0 to 2, right? There's the iterated integral. So that's the setup. And that is worth 70% of the points. But of course, I won't be nice enough to give you rectangular regions on a test. It'll be the general regions, so it's going to be harder than this. I'm going to make life a little bit easier. Going to factor out 4. I am also going to do a nice little trick that is sadly overlooked a lot. Since we're doing with respect to y first, that x plus 4, that entire thing is considered to be a constant. So group it together. X plus 4 is a constant. There's going to be that constant times upper minus lower, which is just 2. Plus a half y squared from 0 to 2. Well, that's just 2. Oops. X plus 5. Yes, it does. Right, so it's 8 times that integral. Half x squared from 0 to 2 is also 2. Right, and then 5 from 0 to 2 is 5 times that length, which is 2. Get 8 times 12 is 96. So there's your double integral. Yes, there's going to be a region of integration. Again, the first thing you want to decide is the order of integration, dx dy or dy dx. Well, technically here, the order doesn't matter. It does. One order is clearly advantageous. Which order would be advantageous? Notice if you do it with respect to x first, it's integration by parts. Whereas if you do it with respect to y first, we may be able to avoid that. I say may. It's not guaranteed. And in fact, here I think it winds up still being integration by parts, which is annoying, but you know, whatever. So y is going to go 0 to pi over 6. X is going to go, oh, oopsies. I drew that rectangle backwards. I need to rotate that. I'd be better off drawing the whole thing. X goes to pi over 6, y goes to pi over 4. So y bounds 0 to pi over 4, x bounds 0 to pi over 6. So you want to look at what we're taking the cosine of. Partial with respect to y is just 1, which is perfect. So the antiderivative with respect to y would be sine of x plus y. Oh, bummer. That sucks. Gotta love when Windows updates and changes the entire layout of the screen. But you should know how to do a single integral by now on Mathematica. You should have learned that in Calc 1, Calc 2. Double integral, very similar. I mean, it's an iterated integral, so it's just going to be nested. Now remember how the iterated integral works? The inner integral is with respect to the first differential, which for us was y. Y will go from 0 to pi over 4. And then x 0 to pi over 6. You are allowed to use technology to evaluate the iterated integral unless I specifically say otherwise. As a general thumb, if I actually just give you an iterated integral, you're not allowed to use technology for it. If it's a double integral over a region, once you set up the iterated integral, you can then just go ahead and plug it into technology. Just be careful. If you plug it in wrong or you copy the answer down wrong and don't show me any work, I can't give you partial credit for the evaluation. Oof, that looks hideous. I wonder. That is probably considered simplify. So what if I do expand? That's still not what I have written down. But I think it's the same.
The input that you put for did you do x times cosine x plus y or x plus cosine?
Times.
I subtracting x sine x.
Top minus bottom. Right, so when y is pi over 4, and then minus when y is 0. So after a lot of calculus and algebra, you should get this. Obviously, you're going to have to do 2 integration by parts. Then you're going to have to do the sum to product formula for sine. Lots of fun. And I'll save you that headache. So there's the final result. And I think that is, if you simplify the Mathematica output, I think you get that. Looks like you will. I actually wonder if it would have been easier to do dx dy and just do a single integration by parts. Who knows? So we want to find the volume of the solid that lies above the rectangle R and below the elliptic paraboloid z equals 49 minus x squared minus 3y squared. Probably should write it this way instead of z. I'll do f of xy. Same thing. So think back to, what was it? Thursday before break? I think that's when we did it. We discussed single integrals, right? So we discussed what the geometric interpretation of an integral is. And we also discussed what the geometric interpretation of a double integral is. What is the geometric representation of that double integral? What about the solid? Don't blame me, it was a long spring break.
Give signed volume.
Gives a signed volume of what? The solid, or the region between the function and the xy plane over that domain of integration R. Positive if it lies above the xy plane, negative if it lies below. We're trying to find volume of a solid, so we're going to want absolute value. But look at this. It's saying specifically it's lying above the rectangle 0, 2 cross 0, 2. Wasn't that rectangle located in the XY plane? So if it lies above that rectangle, it has to be above the XY plane. Perfect. We don't need an absolute value. But it's below the 49 minus x squared minus 3y squared. So volume is going to be the integral over that region R, that rectangle R. Since we're doing technically between two solids, we're going to have to do a difference. So the upper bound is the function z. What's the lower bound for our region or for our solid? The xy plane, which is represented by what? XY plane is the plane z equals 0. Obviously, you're not going to need that minus 0 part. So there's what the volume equals. So there's the integral setup for volume. We now need to set that integral up as an iterated integral. Right? So again, you want to ask yourself, what order do we want to do? dy dx or dx dy? Doesn't matter. We can go with dy dx. Bounds for y. And then bounds for x would also be 0 to 2. So there's your iterated integral setup. Sadly, there's nothing we can factor out. With respect to y, that 49 minus x squared is a constant. So it's going to be the length of 0 to 2 over that times that constant. So 2 times 49 minus x squared. Then it's going to be minus y cubed from 0 to 2, which is just 8. 2 times 49, 98 minus 8 is 90. Right, 90 minus x squared dx from 0 to 2. 180 minus 8 over 3. $180 times 3. 18 times 3 is 54, so it'd be 540. Oh. Got to distribute the 2 to the x squared. I did it to the 49, but not the x squared. So it'd be 2/3 x cubed from 0 to 2, which is 2/3 of 8, so 16 over 3. That should get me what I want. 540 minus 16. 524, right? Volume of a solid would be 524 over 3 cubic, whatever the units happen to be. Oh. Average value. We just look at f of x over some interval, a to b. What was the average value? That's f bar. This was covered in Calc 2. Of course, assuming that f of x is continuous over the interval. B minus A. Isn't that the length of the interval? So it's 1 over the length of the interval times the integral over the interval of f of x. Length of the interval. Just the integral over the interval dx, isn't it? I write it those last two ways to make a connection. So let's extend this to a two-variate function. Well, for Singer-Ver is 1 over the length of the interval times the integral over that interval of the function. What is the two-dimensional measure? Right, the one-dimensional measure is length. What's the two-dimensional?
Is it gonna be the same thing, but just the double integral?
Well, it can't be the same thing because length of a region doesn't make sense. The two-dimensional unit is area. So 1 over the area of your region times the integral over the region of your function. Area of a region is just the integral over that region of the area differential. Right? Much like the length of an interval is the integral over that interval of the length differential. Now, obviously, if our region is a rectangle, area of a rectangle is very easy to find. So we're not going to have to worry about setting up a double integral for that. But if the region was more general, then you would have to set up the double integral. So that's how we're going to find the average value. In fact, out of 7, what is the area of our rectangle? Oh. Oh, that's not good.
40.
40. Probably the easiest area to calculate is a rectangle, right? Length times width. Maybe a circle's easier. Pi r squared. Now we have to set up the iterated integral. Right? We have to decide, do we want to do dy dx or dx dy? I'm gonna do dy dx. Bless you.
Where did you get 40 in the denominator?
It's the area of the rectangle.
Oh, wait.
The anti partial, let's say, of e to the y times the square root of x plus e to the y. Well, if you take the partial of x plus e to the y with respect to y, don't you just get e to the y? Which is what we have on the outside. Factor out that 2/3. Left with 7/60. Integral 0 to 8. That was going to be fun. Evaluate the integrand, y goes from 0 to 5. You should get x plus e to the 5th to the 3/2 minus x plus 1 to the 3/2. Good news is both of those terms, if you look at x plus e to the 5 and x plus 1, their derivative with respect to x is 1. Both are to the 3/2 power. So when you take the antiderivative, you're going to get 2/5 as a constant for both of them. So factor out that 2/5. You have 7/60 times 2/5, which is what, 7/150? X plus e to the 5th to the 5/2 minus x plus 1 to the 5/2. Evaluate that. 0 to 8. Should get that. Nothing we can do with that 8 plus e to the 5th to the 5/2. So just leave it. Really nothing we can do with that e to the 25/2 either. 9 to the 5/2. Same as 3 to the 5th. What's 3 to the 5th? It's 243. 1 to the 5/2. Just 1. Negative 243 plus 1. There's your average value.
how you brought the y radical. That second step there.
Mm-hmm. What about it?
Can you just refresh me on how you got from step one, step two? So
What's the partial of x plus e to the y with respect to y? Just e to the y, isn't it? X plus e to the y with respect to y. That x is 0, right? So dx dy is 0, because x is a constant. And then d dy of e to the y is just e to the y. So you can think of that square root as just square root of u. And that antiderivative is 2/3 u to the 3/2. So 2/3 root x plus e to the y to the 3/2. Oh, not root, I'm sorry. Quantity of x plus e to the y to the 3/2. That's how we got to there. However, that only works if your substitution, the derivative, doesn't involve x's. So if that would have been x squared plus e to the y, we would not have been able to do that. That would have required the use of a Jacobian. We would take the antiderivative of u to the 3/2. It's 2/5 u to the 5/2, right? Both of those terms are going to have a 2/5, so I just factored out the 2/5. And it was 7/60 times 2/5. Question. Now we start looking at more general regions. This is where it gets fun. Want to evaluate double integral of the area differential over the region D that is located in the first quadrant, bounded by the semi-cubical parabola y squared equals x cubed and the line y equals x. you keep popping up, go away. Actually, the first thing I want to do. No, I will do that. Just try and get an idea of what this region looks like. So I'm going to use contour plot. Y squared equals x cubed. And y equals x. Have to set a viewing window, so let's just go rectangle -5 to 5, cross -5 to 5. Don't want the frame. I do want the axes. I'm going to be safe and say the origin is 0, 0. So our region is this little bit in here. So it looks like I thought there's a way I could actually get the point. Sure there is. There. Maybe under drawing tools. Why the beep? Oh dear. No. No, it wasn't that. Ah, get coordinates. I knew there was. Yeah, it looks like it intersects at about 1. Looks like it intersects at 1, which it does. So what I'm going to do, it's probably what, 1, 1? It has to be 1, 1. As I'm now going to go back and I'm going to change this. Viewing window 0 to 1. Oh, you can stay there, that's fine. I don't want R. That is our region D. What I'm going to do is just label those points. I could have done that on the plot, but whatever. We have to pick a way to describe it, either horizontally simple or vertically simple. If I remember correctly, I think horizontally simple is dy dx, vertically simple is dx dy. I think that's the order. It doesn't really matter. So I'm going to go with dy dx, horizontally simple. So again, you draw an imaginary bar. We're going to slide it horizontally. So as we're sliding it horizontally, what is the interval it covers? I'm not looking vertical. I'm looking horizontal. As it moves horizontally, what is the interval it's moving horizontally? Zero to one. It's just the x interval, isn't it? So our imaginary bar slides horizontally from 0 to 1. As it slides from 0 to 1, what does the bar extend from vertically? Right? The y squared equals x cubed to y equals x, right? But we want those as functions of x. So as a function of x, what is that bottom curve? Hmm? That's a function of y. Function of x would be x to the 3 halves, right? Yeah, so if we were doing the other way, yeah, it'd be y to the 2/3. Y will go from x to the 3 halves to x. Now what we're actually doing is finding the area of that region. That would be your setup. I leave it to you to verify that that will give you 1/10. We will look at more general region integrals on Thursday.